So we got to define big O notation. We mentioned at the end of last time that we're mostly interested in broad classes of growth rates. We don't really care so much about the finer details of how fast things are growing. Really just care about like, is this growing fundamentally faster? So n versus n squared versus 2n, uh, n does grow faster. This guy grows faster, but uh, not an important difference in growth rates, right? What about n versus n squared? Whoops. This is an important difference. What about 3n squared plus 5n uh, versus 37n squared plus 28n? Not an important difference. And the reason why, if you've seen any calculus, is that in the case of this and this, these are comparable growth rates. Eventually, with this guy here, it's obvious that this is always just 2 times bigger than this. But with this even down here, um, it's going to eventually look more and more the same. As n gets bigger and bigger, these 2 terms, cease to matter because this guy n squared grows so much faster than n that eventually you're going to end up with 2 curves that compare to each other in the same way that n compares to 2n. You're just going to end up with n squared. This function over here is just going to eventually look like it's consistently 37 over 3 times bigger than this guy over here. Um, and so you're going to end up with the same situation. It's just a constant multiple of the other one, and then we end up back at that linear speedup theorem, which says that constant multiples don't matter. So at the limiting rate, for large n, this situation of this guy versus this guy is kind of the same. Just it's growing faster, but only by like a linear factor. Um, another important distinction would be the square root of n versus n. That's another important difference we need to think about. Another one is like log, log of n versus n. These are important. 2 to the n. That's going to be an important one, and this is going to be much, much faster than n or n squared or n cubed or dot dot dot. Um, so we need to be able to figure out how to talk about this easily, and the key to that is big O notation. So let's see, clear canvas. There it is. Okay, so definition. Um, so let f and g be functions from n to, I guess I can't write there, to r. So they're functions that take natural numbers as inputs and spit out who cares as long as it's a number as output. Um, we say that f of n is in O of g of n if there exists a constant, positive constant c such that um, f of n is always less than or equal to c times g of n for sufficiently large n. Meaning that f of n, this inequality is allowed to be false for the first few n, but there's got to be an n past that such that this is true. So eventually this has got to just be fundamentally always bigger than this. The first few n doesn't matter so much. People tend to abuse the notation and write that f of n is equal to O of g of n. This technically makes no sense, but I'll write it anyway. But really, you should know that O of g of n, this is an equivalence class. What it really is O of g of n is really the class of functions which grow comparably fast or slower than g of n. When I say comparatively fast, I mean kind of in that linear up to a linear constant kind of case, right? Um, so yeah, so that's that. Here's another one. So I mean, you can when you see this comparably fast or slower, you should kind of think in your head like greater than or equal to, right? Comparably fast or slower. It's sort of like greater than or equal to, but not with respect to the amounts, but with respect instead with respect to growth rates. Now let's think about, I would be remiss to define big O notation if I didn't also define little o notation. So again, fg as before. We say that f of n is little o of g of n if little o is just basically more pessimistic. It's the same thing as big O, but without the equals. So you're no longer allowed to grow comparably fast. So the way that we can write that is um, uh, if the limit, this is some calculus. If you don't know calculus, don't worry. We're not really going to use little o for much. I just felt like I needed to explain it. If the limit of the ratio of the two functions is equal to zero, with f in the numerator, meaning that g of n grows faster. So basically, as n gets bigger and bigger, g of n outpaces f of n so that this guy can't keep up and we get a smaller and smaller fraction and we get closer and closer to zero. That's what this is saying. Um, Keep in mind that if you're comparably fast, if you're up to a linear constant, then up here, if f of n is in O of g of n, then the limit as n goes to infinity is of f of n over g of n is equal to c, where c might be zero. So you can kind of relate these two and make the definitions look more close to each other by, instead of writing what I wrote here, instead of writing the limit equaling zero, instead write equals c. In fact, I should probably say, well, I can say, I should say positive constant, but I would say basically um, c greater than or equal to zero um, up there. So little o basically just means that you're slower. So big O of n is the class of functions which grow comparably faster, slower than g of n. Little o of n is really the class of functions which grow comparably which grow slower. Um, if comparable speeds are excluded. So it's really sort of like just strictly greater than. So big O is like greater than or equal to, little o is sort of like just strictly greater. But we're talking about growth rates. So we're sort of defining like this ordering of functions in terms of growth rates. Um, so with this in mind, do we want to do examples? Should I do a couple examples for people? Let's do like one quick example. So as a quick example, let's compare like the square root of 3n plus 8. Let's show that that is O of the square root of n. And this is really the way that we're going to use big O notation. In fact, I'm going to write exactly the way we're going to be using it. I'm going to be saying usually equals because I like to abuse the notation as much as the next person. This is kind of what we care about. This is contained in other classes besides O of the square root of n. O of the square root of n is sort of, it's also, this is a subset of O of n. N grows faster than the square root of n. It's also a subset of, O of 2 to the n. But really, what we're trying to do with the big O notation is we're using it to like pick out the fundamental class that it is. So I could say this, these are technically true, but they're not really what I care about. What I really care about is the sweet spot. What is the function that sort of captures in the simplest form the essence of the growth rate of this? That's really what we're doing with big O notation. So the idea, maybe I should write that. The idea is to substitute for this mess with all the constants and weird stuff and specificity is going on. The function, the simplest function which has the same growth rate as what we care about, in the sense that we care about it. That's what I should say. The same growth rate in the sense that we care about it. That's the idea. So that's how we're going to use big O notation. So if I write, you know, 2 to the 7n cubed minus the square root of 58 and, with a plus sign of n, and then I divide all of that by n or something. Just ignore it. Who cares about any of that? It's 2 to the n. This is the part that 2 to the n cubed, I should say. Sorry. Right. None of the other stuff matters. Maybe the dividing stuff matters. We can ignore the dividing part. How would you prove that this is O of square root of n? My advice would be don't, but let's go ahead and not take that advice. I sort of did a little example here already in Desmos. We're not really super interested in proving this stuff like with much detail, but here's my 12x plus 80, square root of that. I want to show that that's O of the square root of x. Well, you can see if I write that down, I do have something that's always smaller, but I can pick a number. What's your favorite number? Maybe 7. And look, we've got a function that's always bigger past 1, But, meanwhile, though, if this was the square root of x squared, if I did that, that would not be, so let me go ahead and say that actually. The square root of 3x squared plus 28, that is not O of the square root of x. What it is it's O of x itself. The square root and the squared kind of cancel out. And you can see that. You can see that because just look, it gets out of control. And you can obviously see that, like, no number that I put here, even if I put like 100, that'll work for a while. That'll work for a while. That'll work for a while, but eventually, look, it doesn't work forever. I could put 500. It'll work for a while. It'll work for a while, but nope, not forever. It's always going to be the case that this guy eventually outpaces this, no matter what number I put here, because it grows at a fundamentally faster rate. But if I just put x, then let's lose the 500. Let's not even use 500. Let's just use x. Even here, eventually, well, okay, that's not going to work. Maybe 3x. What's the square root of 12? Square root of 12 is like what? A little over 3. So let's say 4. There we go. 4x grows faster. You can see that there's my constant c. So if we're connecting back to the definition, does there exist a constant c such that the square root of 12x squared, is always less than or equal to c times x? Yes, there does. Just take c to be equal to 4, like I did here. And you can see that you do have something that's consistently, bigger. So that's the idea behind big O notation. it's not don't I don't want people to worry too much about it. It's something that we have in order to talk easier, in order to make our discussions simpler. Um, Now, big O is the dominating kind of force in terms of what's going on. We're very rarely going to use little o if ever, but we will occasionally use big O's sister. I will write that down. Big omega. Um, so it's just the same, but for less than or equal to. So f of n is in omega, big omega of g of n, if um, there exists a positive constant c such that f of n is always greater than or equal to the other way around, c times g of n. So uh, big big omega. So I should say omega is to best case as O is to worst case. That's how big omega is used, and that's why we do need to probably define it. Big omega, this notation shows up very rarely because it's usually very hard to prove best case complexity. It's really hard to, say I have an algorithm that accomplishes something for me. It's extremely rare and difficult to prove that that algorithm is optimal. There's very few cases of that. There's a couple of them, but those would be naturally where you see uh, big omega being used is in those optimality proofs. Um, there is one maybe coming up shortly if I decide to go through it, but aside from that, I'm only aware of like two. So typically, we're interested in big O notation more than any of these other things.